This example is one about force on magnetic material. I really love this example because it pulls in quite a few different elements of physics and electromagnetics. It's got the magnetic circuit idea, which you should know by now that I like a lot. But it also has essentially work. We're gonna do something useful. We're gonna apply this thing now. And so let me just read it to you. We've got a U-shaped electromagnet that's designed to lift a mass placed on the keeper. So we've got this yoke and the keeper as shown, and the iron yoke has a relative permeability of 3000 and a cross-section of 40 square centimeters and a length of 50 centimeters. So the length is around the yoke, right? And the air gaps are each 0.1 millimeters long. Neglect the reluctance of the keeper, whose mass is 50 kilograms, and determine the number of turns required to lift a mass of 350 kilograms when the current is 1 amp. So that's pretty neat. So essentially we're levitating this mass m, and we're going to put the mass in the middle so that we don't have any sort of mechanical torque, right? We don't want this thing to rotate. We don't need to be worried about that in our course. So all right, let's first draw the circuit, right? So we're electrical engineers, most of us anyway, and so let's draw the circuit. So the N turns carrying current I create a magnetic potential Vm like this, and then we go this way. And really, I could put the reluctance of the yoke on either side of this potential, but I'm going to put it right here. So I'm going to do this with kind of a script R subscript Y for yoke, and then we hit a gap. So I'm going to put the reluctance of the gap here. All right, and then we're told to ignore the reluctance of the keeper. And so then I have another reluctance of the gap. And so I already put the reluctance of the yoke. So then I come back to my potential. And so this is my equivalent magnetic circuit. Pretty cool. And then I'll say that I've got some current, if you will, or some flux through this circuit psi. All right. Now, in order for this thing to move, to support the mass, then in the y direction, the magnetic force, right, or at least we'll work in terms of magnitudes here because this is the y direction, positive y. The magnetic force has to be greater than the mass of the object plus the mass of the keeper times gravity. So that's Newton's law there. Okay, and in a lecture video, previous video, we showed that each one of these little forces is 1/2 b squared s over mu 0. And so each one of them is 1/2, and so together they make b squared s over mu 0. So I'll write that down. B squared s over mu 0, like that. And so that has to be greater than capital M plus little m, the total mass, right, the keeper and the mass, times gravity. Okay, so now if I work this a little bit, and all of these things are positive, so I don't need to, s, the area, mu 0 is positive, mass is gravity. We're taking gravity as 9.8 because we've already said that this is in the negative direction, so the positive direction has to be greater than the negative direction. And so I don't need to worry about flipping this inequality as I manipulate this a little bit. So in fact, we're not even going to worry about gravity for right now. So if I solve that, if you will, for b by multiplying by mu s, dividing by s, and then taking the square root, I see that b has to be greater than mu 0 times m plus little m times g over s, right? So that's what we get. And then I'll remind you, as we've seen many times now if you're watching the example videos, but I'll say it again just because they are optional, these example videos. The flux is the integral of b dot ds. And so we've got these coils, and they produce a flux that is parallel to its axis, the coil's axis, that is. So this is B. And the cross-sectional area, that vector is also in this direction. So they're parallel. B and ds are parallel. So the integral then is just B times S. And so that's the flux. And so I can relate this to flux, and I can say that the flux then must be greater than, because B is the flux divided by S, so the flux has to be greater than S times the square root of all that stuff. Okay, so that brings in the flux to this equation. So just to be clear here, I'm making the substitution that B, the magnitude of the flux density, is the flux divided by the area. So I'm making that substitution in here and then multiplying by S. All right, now let's talk about those reluctances. So the reluctance of the yoke is the length of the yoke divided by mu 0 times mu r, the total permeability there, times the cross-sectional area of the yoke. And do we have all of that? We have the length of the yoke, yes. We have the area of the cross-section, yes. And we have its permeability. So we've got all of that. And the reluctance of the gap, so this is each gap, is the length of the gap divided by mu 0 s. So of course we have all of that in the problem as well. And so the total reluctance of our circuit, if you will, is the reluctance of the yoke plus 2 times the reluctance of the gap, because all of these reluctances are in series, and series reluctances or series resistors, if you were thinking that way, add together. And so they each have a mu 0 s in the denominator. So I can pull out mu 0 s just to make the calculations a little bit nicer, and I have the length of the yoke divided by mu r plus 2 times the length in the gap. Right, so 1 for each gap. Okay, so now I'm going to try to pull together all of this stuff. So I know from Ohm's law now that the flux, or if you're thinking of in terms of current, the flux psi is the magnetic potential divided by the total reluctance. So this is Ohm's law. Let me just write it out here. Vm equals the flux times the total reluctance. So think about this as voltage equals I times R, right? And so this tells me that the flux is the magnetic potential, right, divided by the total reluctance. And we have these things. And the magnetic potential, right, again, is due to the coils. So this is related to the linkage. So each coil, there are n coils, has a current I. So that is the magnetic potential, n times I, divided by the equivalent reluctance, which we have, right? And so this thing, because this thing is psi, right, this is the flux, we're saying. So this thing now must be greater than or equal to this over here. S times the square root of mu 0 m plus m times gravity over S, like that. Okay, and so what I'm after is the number of turns. How many turns do we need, right? So I can certainly multiply both sides by Req, or script R, and script R is positive. Divide by the current. The current's positive, so I don't need to switch the inequality sign. So what I get is that n has to be greater than 1. Did I miss a mu 0? Let's see. Oh no, yeah, so here's the reluctance, the total reluctance. So I'm going to multiply both sides by the total reluctance, so I've got that here, and that s will cancel with this s, actually. So I've got 1 over mu 0. Then I divide by I, so I've got an I down here. And then I've got this thing from the reluctance, Ly over mu r plus 2 times the L gap times, then I need the square root business there, mu 0 plus capital M lowercase m times gravity is 9.81 over s. Right, s is in the square root. And so I plug in my numbers, I'll leave that to you, and I see that n has to be greater than, and it actually turns out to be 323 point something. So, 323 point something. And so what we'll say is that the minimum number of turns there is, because you can't have a fraction of turns, right? And so the minimum number of turns is 324. That is a really cool thing. Magnetic levitation.